Today we discuss birth and death processes. Assume that we have a population with n individuals. Those could be people, those could be animals, they could be plants in a queuing system, they could be customers, they could be a list of tasks for people or for computers, they could be financial assets, they could be a lot of different things. A birth means an increase in the population of size 1. A death means a decrease in the population of size 1. We're going to assume that the birth rate is lambda sub n, and we will assume that the death rate is mu sub n. So that's the number of births per unit time when there are n individuals, and mu sub n is the number of deaths per unit time when there are n individuals. We will assume that the time until the next increase is exponentially distributed with rate lambda sub n, which means the expected time until the next increase is 1 over lambda sub n. We will assume that the time until the next decrease is exponentially distributed with rate mu sub n. In other words, the expected time until the next decrease is 1 over mu sub n. Note that there's a subscript n on the birth rate and the death rate, and what this means is that the rate can change depending on the population size. So if we're actually talking about births of people, a city the size of Toronto has a higher birth rate and a higher death rate than a city of the size of Windsor. Our state diagram, the states are 0, 1, 2, 3, etc. Our state diagram has this appearance. This is a birth, another birth, another birth, death, death, death. So those are the death rates. So this diagram marks the states and the birth rates and the death rates. We are going to define pi sub I to be the long-run probability of being in state I. We also refer to these as the limiting probabilities, and we also refer to them as steady state probabilities. These pi i's are important. They give you characteristics about the system. These are measurements that are important. These are performance measurements. And we use them in various ways. We may want to use them to find the expected position in the system. We can use them in a number of ways. So the question arises is, how do we calculate the pi sub i's? And the way we're going to do it is we're going to use a conservation property. And if we have a stable system, in other words, one that is not periodic and one that doesn't just keep on getting bigger and bigger and bigger, then the overall rate from state I to state I plus 1 should match the overall rate from state I plus 1 to state I. Now, the rate that you're going from I to I plus 1, in order to move there, you have to actually be there. So the overall rate from state I to state I plus 1 is the probability that you start there, pi sub I, and then you have a birth. And the overall rate from I plus 1 to I, you have to start there, and then you have to have a death. So we get this expression here, lambda I pi I is equal to mu I plus 1 pi I plus 1. And we can actually solve using this equation. Now we're going to look at this this is true for all I equals 0, 1, 2, 3, etc. And we're going to look at it in some of those special cases and see that we can actually solve for things. We now look at special cases of that conservation property. In particular, we have lambda 0 times pi 0 is equal to mu 1 times pi 1. We can change the subscripts and we get lambda 1 pi 1 is equal to mu 2 pi 2, etc. And we can keep on changing the subscripts, moving them up by 1. If we look at that first equation, we can solve for pi 1 in terms of pi 0. And what we get is lambda 0 over mu 1 times pi 0 is equal to pi 1. In a similar way, we can solve the second equation and get essentially the same results with just the subscripts moved a little bit. And we get the result that pi 2 is lambda 1 over mu 2 times pi 1, but we already know pi 1. So if we substitute for pi 1, we get lambda 1 over mu 2 times lambda 0 over mu 1 times pi 0. And you can see we're getting a kind of series here, a product chain in front of the pi 0. If we go one more step, if we find pi 3, we would have 3 terms in front of the pi 0. And in general, if we go to the pi sub k, we'll get a product of k terms in front of the pi 0. And the k terms will be, in the numerator, you'll get lambda 0, lambda 1, all the way up to lambda sub k minus 1. And in the denominator, you get mu 1, mu 2, all the way up to mu sub k times pi 0. The thing that's missing here is, yes, we've solved for the general pi sub i's if we know what pi 0 is, but we do not know pi 0 here. How do we find pi 0? That's the next question. And the way we do it is that we use the fact that the sum of all the probabilities, the sum of all the pi sub i's, has to be equal to 1, because those are mutually exclusive events that cover the whole space.